The determinant of a square matrix, determinants are only defined for square matrices, the determinant of a square matrix A is a number, and we denote it with det A, or with these bars that look like absolute value bars. And this number contains important information about the matrix A. For example, it allows many questions about matrices to be converted into questions about numbers. And of course, questions about numbers are much simpler. They can often be answered with simple equations and so forth. So let's see. The definition of a determinant, though, is a bit complicated. So in this video, we're going to look at the definition, and then in later videos, we'll look at how to actually compute them. So the first thing that we're going to need is a permutation matrix. So a permutation matrix is a matrix that has exactly 1 1 in each row and zeros everywhere else. So, but there's another way to define it as well. So a permutation matrix, and I'll denote it with the lowercase sigma, which is standard for no reason that I know of. So sigma is one that comes from the identity by doing some number of row swaps. And let's say we did k row swaps, the basic elementary row operation. And then we say that its sign, or parity, is -1 to the k. So this is, and we denote that by sigma, or sorry, sine of sigma, like that. That's the notation for it. So the identity comes by 0 row swaps, so it would have sign +1. If I had an elementary matrix, I came by doing a single row swap, then it would have sign -1 to the power 1, so it would be have a negative sign. Okay, and so as I mentioned, a permutation matrix is therefore going to have so sigma will have a single 1, so 1 1 in each row and 1 1 in each column, and zeros elsewhere. So that's another way to think about what these things look like. Okay, so for example, if we're looking at a 3 by 3 matrix, perhaps we have 0 0 1 1 0 0 0 1 0. Okay, so this one comes from the identity by doing, let's see, I could swap row 2 with row 1, and then row 1 with row 3. So 2 row swaps. So the sign of this guy would be +1. Okay, and it's possible to obtain this sigma from the identity by some other sequence of swaps, but no matter what, the key point is it will always be even. Whoops. Okay, and so this notion of parity or sign is well defined. Okay, so what we're going to use the permutation matrices for is a precise way of selecting one entry from each row of a matrix and one entry from each column of a matrix. And we'll do that with a permutation matrix. So let's see. So I'm going to define an operation. So if I've got some square matrix, and I'm going to define it by example because I think that's the easiest way to see what's going on. So for the matrix 2 6 7 -1 1 4 0 -2 3, we will define this symbol sigma circle dot A. This is something I made up. You won't find it in the book. You won't find it online, whatever. It's just a cheeseball notation for saying, okay, let's look at sigma. Sigma says we're interested in this entry and this entry and this entry. So that's how we choose an entry from each row in each column. So over here in A, that corresponds to this 7 and this -1 and this -2 right here. And so sigma circle dot A is going to be multiplied together those entries. So you select the entries of A according to sigma and then multiply them together. Okay. Then the determinant of A is defined to be, well, I'm going to pick a permutation matrix and pull out the entries of A according to that permutation matrix. And then I'm going to multiply by the sign of sigma, so it'll get a plus or minus sign accordingly. And then I'm going to add all of those up, where I'm summing over the set of all possible permutation matrices. Okay. So that sum is over all possible permutation matrices. Okay, so let's just look at an example of what this looks like in the 2x2 case. So we'll do one that you know and love, A, B, C, D, just the general 2x2. Now, for something this simple, there's only 2 permutation matrices. We can have either the identity or we can have the off-diagonal. And those are the only 2x2 permutation matrices they are, because there's not a whole lot you can do with a 2x2. Okay, so in this case, so we're going to be summing over just these 2 matrices. Okay, so our capital sigma will only have 2 things in it. Okay, so then the determinant of A is going to be, so for sigma 1, that one comes with a +1 parity, so that's the sign of it. And then we have sigma 1 circle dot A, and then we have a -1 times sigma 2 circle dot A. And so for the first one there, we have, well, here I'll just draw some little doodle. This is not actually even proper math. Here, I guess I can get away with that guy. And I'm going to put in, okay, so it's the product of these ones here as selected by sigma 1 minus the product of these ones here as selected by sigma 2. So this gives us AD minus BC. And yeah, I'm a little unhappy because that second line looks like a difference of matrices, and it's not really supposed to. So let me put some weird bars around it so that you know that this is like makey-uppy land. Yeah, here we go. Quotation marks. Okay. Anyway, main thing is we get the AD out of the first one and the BC out of the second one, and the second one comes with a minus sign, so the grand total is AD minus BC. All right. Okay. So that's the definition of the determinant. Coming up next, we'll look at some ways to compute the determinant that do not involve any of this junk, permutation matrices, sums, signs, any of this business.